Let's see some Matlab demo with which we can understand these convolutions a little better. This code is available to you. You can take this code and then play with this, change different signals, and then see what happens. The first thing that we'll do now is try to convolve a rectangular signal with a rectangular signal itself, and then see what the output is. As you can see in this animation, what is happening? So we have a rectangular signal x of t, okay, and another rectangular signal which is h of t. So one of the signals, in this case x of t, is fixed in time, that is x of tau is the signal which is inside the integration, tau is the variable of integration, that is fixed. As you can see here, the blue dotted line says that that is fixed in tau. And what are you going to do? You are going to flip h of tau and move it from minus infinity to plus infinity. That's what you saw in this animation, right? It moves from the left to the right. So as it moves from the left to right, you can see what is happening. So at every point it is getting multiplied. The red and the blue are getting multiplied. Whenever there is no overlap, the output is 0 because the product has an area which is 0. And the yellow part shows the area under the product, and then that keeps increasing as long as there is a non-zero overlap, and then it decreases once again when the overlap decreases. So clearly this follows our property that we saw, that the output is always going to be within the limit of t1 plus t2. The input signals had a time duration of 1 second and 1 second, and the output here has a time duration of 2 seconds. Okay, now let us try to convolve this with a non-symmetric signal. So now we have here x of t, which is a rectangular function, and the h of t, which is now the non-symmetric signal which we often keep seeing in our examples. Now same thing, flip h of t. You can clearly see that h of t is now flipped, and then it is moved from left to right. As long as there is a non-zero intersection, the area is non-zero, and then you get a non-zero value as the output. When the intersection is 0, then you get 0 as the output, right? So this is the output when you convolve our two signals together. Once again, here you can see that the output time duration is the sum of the time duration of the input two signals. Now let's try and convolve two signals out of which one has infinite time duration. So as you can see here, we are convolving a step function with a rectangular function. Step function has infinite time duration, which means the output also should now have an infinite time duration. Let's see if that is happening. So the step function is flipped, that is time reversed, and then it is moved from the left to right, that is what is happening. And then we are seeing what happens to the area of the product, and that starts becoming non-zero at minus 0.5 and then keeps increasing, and then it stays non-zero infinitely long. This is exactly what we expected, and that's what we are getting. Okay. Let's see what happens when we convolve the rectangular signal with the impulse signal. So as you can see here, the impulse is time reversed, which is exactly the same because it's an even signal, and it is moved from left to right. So it's 0 till there is an intersection, and when there is an intersection, remember, all you're going to do is just sample each and every point. It just takes each and every point, and the area is going to exactly be the value of the signal itself, which is basically sampling the signal at every point, and then the integration is putting things together. So you get the same signal once again. Okay, so convolving with an impulse is going to give you the same signal itself. So it's like an identity transformation. You don't do anything to it, you just give back what was given as the input. Now let's see what happens when you give our non-symmetric signal. So we are convolving the impulse with our non-symmetric signal. as before, whatever is the input is what we are getting as the output, because we are convolving only with the impulse. Now let's see something interesting. We'll convolve the rectangular function with a cosine signal. As you can see here, what is happening, the cosine signal is time reversed and it is moved from left to right. But you don't see anything moving simply because the cosine signal is infinitely long and it is moving from left to right. So you can see this movement happening, but the signal is actually infinitely long. But the output is now 0. Why is the output 0? If you think about it, what is happening here? The rectangular signal is of duration 1, which is exactly equal to the period of the cosine signal also. In other words, at each and every point, all you're trying to do here is nothing but compute the area of the cosine signal within a time duration which is exactly equal to the period. And remember what we studied when we saw about periodic signals. You can take the area of the periodic signal in any time duration as long as the interval is exactly an integral multiple of the period. The area is always going to be the same. Now, what is the area of the cosine signal in one time period? It is 0. Because the area of the signal in one time period here is 0, because remember there is equal up and down shifts. No matter where you start and end, as long as the time duration of the integration is exactly equal to the period, which was the case here because the rectangular window was of size which was equal to the period, the integration output was always 0 because the area was 0 and we always got a 0 signal. So now this also confirms our property that we said the convolution of two signals will give a maximum time duration of t1 plus t2. In this case, the maximum is infinity, but it's not always necessary that the convolution output should be equal to the maximum. Here we got a signal whose duration was actually 0, right? So it can be anywhere between 0 and infinity, that is 0 and t1 plus t2. We saw an example where now it is 0 and we also saw an example where it was t1 plus t2. Now let's modify this case. What if the period of the cosine signal was not equal to the window size or the rectangular signal size? If we change that, then we should see a non-zero signal at the convolution's output. Let's see if that happens. So I'm going to change the period of the sinusoid. Now you can see that the rectangular window has a duration 1 second, whereas the period of the cosine signal that we have here is less than 1 second. So because of which the convolution has now a non-zero output. So now what we have done is we have verified several properties. Now let's verify what happens when we convolve a signal by an impulse which is shifted by some amount. Okay, so let's try and shift the impulse by some amount. Let's say I want to shift the impulse by some amount which is equal to, let's say, 1 second. So here we have an impulse at 1 second and we are convolving that with a rectangular function. So let's see what happens when we convolve these two. As you can see here, the area is 0 till you have a non-zero intersection. The non-zero intersection started only with the shift of +1 here. So the signal is now centered at +1. So the rectangular function which was centered at 0 now got shifted to +1. Let's see what happens when you have a non-symmetric signal. You should see this same thing again. So you have an impulse at +1 and you have the signal existing from -1 to +1. Once again we have the same thing. There is a shift which is happening and we'll see the entire signal to be now centered at +1 instead of 0. So you have this code which is given to you. You can play with this code. You can change different signals. You can add your own signals. You can add your own kind of systems that you want to represent here by putting in its impulse response and then see what happens to the output. You can play with it, then see what happens.